Right, let's jump right into this explainer. Today we're unpacking a highly rigorous architecture called the three-layer approximation. Now, since we're targeting systems engineering and AI postgraduates here, I know you're all too familiar with the persistent headache of designing autonomous systems. We are constantly trying to bridge deterministic safety with probabilistic adaptability, right? Well, this paradigm does exactly that. It seamlessly unites Rust's raw bare metal execution power with the nuanced semantic decision making of large language models. So, if you're trying to figure out how to structure this bridge to mitigate hallucination creep and really optimize your agentic workflows, this is absolutely essential. Let's dive in. Here's a quick roadmap for our session. We'll start with a high level view of the three-layer approximation, then drill down into layer 1 for state and memory, layer 2 for execution and tracing, layer 3 on optimizing to argmin(x), and we'll wrap up with the litmus test validation. Okay, part 1, the three-layer approximation, mapping out this agentic ecosystem. So, in complex systems, we're always battling between the need for pure speed and the necessity for adaptable intelligence. In this architecture, Rust is our engine. It gives us that strict, deterministic tracing we literally have to have for efficiency. The LLM, on the flip side, acts as our director. It operates against predefined system prompts to make those messy, abstract decisions that hard-coded logic just can't handle. As postgrads optimizing these agentic workflows, you know all about computational overhead and the very real dangers or probabilistic drift when relying on language models. By isolating the semantic choices inside the LLM and forcing the actual execution into a bare metal environment like Rust, we're basically creating a firewall. It's this beautiful synergy of computational muscle and probabilistic mind. Let's move into how this actually starts in layer 1, state and memory, which acts as the logic gate for the whole architecture. At this foundational level, we're looking at extreme computational conservatism. First, the system reads the source. Then it evaluates a strictly enforced conditional. We are only building logs with Rust if, and only if, the diff is unknown and totally absent from our state tracker, memory.md. Let's ground this for a second. Imagine you're parsing some massive distributed system config file where, honestly, 99% of the states stay exactly the same between epochs. If the state is unchanged, memory.md is our base case. That massively saves on compute overhead because you aren't spinning up resources for no reason. It's only when we hit a true diff, a genuine unknown, that the system pivots and actually queries the LLM for the next tool call. It's an incredibly efficient entry point designed specifically to kill resource waste. But here's the catch. Once that semantic selection is actually made by the LLM, once it says, use this tool, how do we bridge the gap between that probabilistic logic and our strict deterministic performance? Like, how do we precisely trace the issues that inevitably pop up during execution? Which brings us perfectly to layer 2, execution and tracing. This is the real performance engine of the system. Notice the architectural handoff we have going on here. The LLM generates a semantic tool callback statement based on its probabilistic read of the goal. But because probabilistic models are, frankly, terrible execution environments, Rust takes the baton. Think about the mechanics for a second. The LLM might spit out a highly structured JSON response detailing the tool and parameters, right? Well, Rust then takes that, parses the JSON directly into native structs, and executes the callback natively. This is a brilliant separation of concerns. The LLM is only responsible for the what and the why, while Rust owns the how. Relying on a strictly typed, compiled language to handle operations totally mitigates your risk of execution failure. Now, Rust isn't just firing off the tool blindly. That would be a total waste of its bare metal capabilities. Instead, as it executes that native callback, Rust actively traces the resulting issues. And in a systems engineering context, this tracing is incredibly granular. We're talking microsecond level execution times, memory heap allocations, deterministic error rates, the whole shebang. It meticulously maps out an optimization curve based on these heart metrics. So Rust is simultaneously executing the action and generating the exact diagnostic telemetry we need to track performance over time. So, we've got this optimization curve mapped out by Rust's granular tracing. The next logical question is, what is the endgame? How do we take this raw diagnostic data and actually drive this machine learning architecture toward a definitive mathematical convergence? All right, layer 3. This is where we optimize to argmin(x) and hit that mathematical convergence. Here in layer 3, the system ingests that granular curve we just talked about. It then iteratively fits the target optimization until it reaches argmin(x), the argument of the minimum. In this specific setup, reaching that mathematical minimum is not just some theoretical whiteboard concept, it is concretely anchored and proportionally bound to our unit tests. The architecture just loops through successive epochs, refining its approach based on the tracing data, driving that loss function down. By tying argument x directly to unit test proportionality, we guarantee that mathematical convergence actually means verifiable functional stability in your codebase. Now, these unit tests that are proportional to argument x, they consist of three distinct computational components. First, you have the tool query itself, that initial semantic request. Second, the physical execution by Rust that generates our telemetry. And third, the agnostic code. For those of you actually building these systems, this agnostic code is absolutely crucial. It acts as the neutral interface between the semantic layer and the deterministic layer. It's the decoupling mechanism. It ensures the LLM's logic and Rust's execution don't get so tangled up that they lose their modularity. Our optimization curve is iteratively fitted against these specific isolated parameters. Finally, Section 5, the litmus test validation, where we close the loop. Obviously, we can't just let this architecture run indefinitely in a black box. After iterating through automated epochs to fit that curve and chase the target optimization, the system intentionally hits the brakes. It reaches what's defined as the litmus test end, and right at this moment, the system queries the user. As systems engineers, you know this is a massive safeguard against optimization drift. We've all seen automated pipelines perfectly optimized for the wrong objective function, giving us a mathematically flawed but practically useless result. This query makes sure the theoretical minimum achieved by our Rust LLM combo actually aligns with real human-defined success before it commits to the next state. Which leaves us with one final structural thought to chew on as we wrap up this explainer. We know the system pauses to query the user, but if that litmus test validation requires an adjustment, how does that resulting feedback filter all the way back up to alter the memory.md state for the very next lifecycle? Think about how human validation continuously shapes the base case of this entire three-layer system. It's a fascinating challenge. Thanks for joining me for this breakdown. Keep exploring and keep optimizing.